welcome everyone. Till now, we have discussed a lot about design tensile strengths of wide flange, channels, angles, and built up sections. Let us now look at rods and bars. The basic difference between a rod and a bar is that a rod is always circular in shape, while a bar can be rectangular, square, or circular in shape. You can say that a circular bar is also called a rod. Well, we will discuss two topics here. First, we will learn what are threaded rods and discuss how to calculate the design tensile strength of threaded rods. So let's begin. Threaded rods. You might have seen this before. It has a circular cross section and has protrusions or threads on the rod. This is a threaded rod. It is mainly used in bowls in this manner. Here you can observe the threaded rod here. Let us go over some terminologies for a threaded rod. This part of the bolt where there are no threads present is called a shank, and the part of the bolts where threads are present is called a thread or a thread runout. As you can see, the shorter bolt does not have a shank, so a bolt can come with or without a shank. I hope these two terms are clear. Let us discuss more about threaded rods. This is a magnification of the threads. You can see different terms labeled here. Let us discuss them one by one. This is the surface of the thread, which is magnified even more. Well, let us start with pitch or P as shown in both the figures. Pitch is the horizontal distance between the adjacent threads. Next is thread angle. It is the angle subtended by two inclined surfaces of two adjacent threads. As you can see in the figure on your right, the thread angle in this case is 60 degrees. Next is the root of the thread. As you can see in the figure, the root is the inner part of the thread, or you can say that it is a trough of a thread. Roots are present on both the sides of the rod, and the vertical distance between the two roots of a thread is called a minor diameter or minimum root of the thread, denoted by an uppercase K. As shown, AISC uses the term minimum root and not minor diameter. The outermost part of the thread is called the crest of the thread. Think of it as a crest of a wave, as crest is the uppermost part or the peak of the wave. In the similar manner, crest is the outermost part or the peak of a thread, as shown in these figures here. And the vertical distance between the two crests is called the major diameter or the major thread diameter. If you observe more closely here, the diameter of the shank is equal to the major thread diameter. Diameter of shank is also called the diameter of bolt itself. Therefore, in this case, the major thread diameter is the diameter of bolt, D. As you can see, AISC table 7-17 gives us the thread dimensions for different bolts. First column is the bolt diameter, D, which is also the major thread diameter, that is the vertical distance between the two crests. Next is the minimum root, K. It is the vertical distance from the roots of the thread, also called minor diameter. Next is the gross bolt area. This is nothing but the circular cross-sectional area with diameter used as the bolt diameter. So, for example, look at the first row of the table. For a bolt diameter of 1/4 inch, the area would be pi d square by 4. So if you substitute d as 1/4 inch, you will end up getting 0.049 square inches, as shown in the table. Next is the minimum root area. This is nothing but the circular cross-section area considering the minimum root distance as the diameter. As in the gross bolt area, we use the bolt diameter D. Here, we use the minimum root distance K to compute the area. As you can see, the minimum root distance is smaller than the bolt diameter. Hence, the minimum root area is also smaller than the gross area of the bolt. Next is the net tensile area. It is calculated with this formula mentioned at the bottom of this table, where D is the diameter of bolt, which is the shank diameter, and N is the number of threads per inch. Design tensile strength of rods. Now that we are aware of the terminologies associated with threaded rods and how to fetch thread dimensions from AISC manual, the next step is to learn how to compute the design tensile strength of rods. As we have learned, the design tensile strength for any element is the tensile stress in steel times the cross sectional area. Well, the nominal tensile stress of bolt has a slight modification. According to AISC J3.7, which I will attach as a reference to this lecture, the nominal tensile stress of the bolt is equal to 75% of the ultimate tensile stress of steel. So, for example, if the bolt is made from a A36 steel that has an ultimate tensile stress of 58 ksi, the nominal tensile stress the bolt can carry is only 75% of 58 ksi, that is 43.5 ksi. I hope it's clear. Next, to calculate the bolt tensile strength, we need its area. As we know, the circular cross-sectional area is just pi d square over 4. D is the bolt diameter. It is calculated as a diameter of shank for the bolt, which means the diameter of the unthreaded part of the bolt. AISC table 7-17 gives us the bolt area of various standard available bolts. I am referring to the 2022 version of the AISC 360, released recently. Now that we have the nominal tensile stress and the bolt area, we can calculate the nominal tensile strength of the bolt. It is the nominal tensile stress of the bolts discussed earlier times the bolt area, or the gross bolt area AB. Design tensile strength is the nominal tensile strength times the resistance factor. Resistance factor to use here is 0.75. I hope it is clear. We will use what we have learned here to solve an example in the next video. See you there.